All right, in the previous video, we kind of looked at the background and basically how mass spectrometry works. In this video, we want to look at a little bit more at the details of how we analyze the mass spectrums. Okay, so just to recap, the x-axis basically represents the mass of the fragments that we're detecting, and then the height of the peaks on the y-axis tells us how much of that particular fragment we've detected. All right, so one of the most important things that we look for in the mass spectrum is the parent ion peak. Sometimes it's also called the molecular ion peak. And this is the heaviest peak in the mass spectrum. You can see how we abbreviate it here. The parent ion peak tells us the molar mass of the compound. And so oftentimes we're using mass spec when we don't know the molar mass of the compound, but we can actually compare it. In this case, we do know that this is the mass spectrum of pentane. And so pentane is C5H12, and so 5 times 12 for the carbons is 60, plus the 12 hydrogens gives us 72, and so this is the parent ion peak, and it corresponds to the molar mass of the compound. Now you may be asking yourself, what about this little peak here? Well, this is due to the presence of the isotope carbon-13. So if you remember, atoms can have different isotopes, right? So this is where they have the same atomic number but different numbers of neutrons. And so the vast majority of carbon is carbon-12, but due to the presence of a small amount of carbon-13, we often see this small peak, just one mass unit to the right of the parent ion peak, and we can just ignore it. It's just due to the presence of carbon-13. So again, the parent ion peak is the heaviest peak in the mass spectrum, ignoring the small peak just to the right of it that's due to carbon-13, and it tells us the molar mass of the compound. All right, a different peak that we often talk about and we like to identify in the mass spectrum is called the base peak. And the base peak is just the one that has the largest abundance. So in pentane, this would be the base peak, just the one that's the highest on the y-axis. And the base peak is significant because it represents the most stable fragment the molecule breaks into. And so often in more advanced analyses, this can tell us a good deal of information about our compound. Now, the base peak is usually not the same as the parent ion peak, as we see in the pentane that we've been looking at, right? This is the parent ion peak. That is not the same as the base peak. But it is certainly possible for the parent ion peak to be the most abundant fragment. This is the mass spectrum of benzene, and benzene is super stable. It doesn't fragment very easily, and so in this case, the parent ion peak is the same as the base peak. And so while this can happen, it is not the norm. So we can also get structural information about our molecule by analyzing the molecular fragments. And often, rather than looking at the mass of the fragments themselves, we look at the difference between the mass of the fragments and the mass of the parent ion. And so the notation we often use is m minus whatever, where this 15 is the difference between the mass of the parent ion peak and the mass of the fragment. And so just as an example, if we chop, so here's pentane that we've been looking at. If we chop off this methyl group, well, this methyl group has a mass of basically 15, right? 12 for the carbon and 1 for each of the hydrogens. And so if we chop off this methyl, the fragment we would expect to appear at m minus 15. And we've said the molar mass of pentane is 72, so 72 minus 15, that would happen at 57. And so if our molar mass, or our parent ion peak, is at 72, and we have a peak that's 15 less, that is most likely due to the loss of a methyl fragment. Or the loss of an ethyl fragment often will correspond to an m minus 29, right? Because this ethyl fragment that we chopped off, so we're detecting this is the piece that we lost. It has 2 carbons, that's 2 times 12 is 24, plus the 5 hydrogens, that's 29. So if we detect this fragment, we'd expect it to appear at the parent ion peak minus 29. Or chopping off a propyl gives us an m minus 43 peak. Or chopping off a butyl gives us an m minus 57 peak. And so by looking at the difference between the mass of the parent ion peak and the mass of our fragment, this difference can tell us what the likely fragments are. So if we see an M-15, probably due to the loss of a methyl. So that means there's a methyl group in our compound. Or if we see an M-29, that's likely due to the loss of an ethyl group. So there's a good chance that there's an ethyl group in our compound. And so this is just showing the mass spectrum we were kind of talking about last time. Here's the parent ion peak at 72. This peak at 57, right, when we calculate the difference between this peak and the parent ion peak, we get 15, and we say, oh, that's probably due to loss of a methyl. This M-29 is actually the base peak. That's due to the loss of an ethyl. M-43, loss of a propyl, or loss of a butyl with the M-57. Now, I do want to take just a second. This isn't something that we're going to go into too much detail, but if you take additional chemistry courses, you're likely to encounter mass spectrometry again. And so we do want to talk a little bit about why something might be the base peak versus something else. So lots of different possible fragments are possible, and we saw, for example, for pentane, that we did get lots of different fragments. But the base peak is typically the most abundant fragment because it's the most stable fragment. And this is something we'll talk about in later on in the semester. But one thing that we're going to learn is that a tertiary carbocation is more stable than a primary or secondary carbocation. So if we ran a mass spectrum on this molecule, if we were to chop off this methyl, we'd have a positive charge on this carbon. It's connected to one other carbon, and so that would be a primary carbocation, which isn't very stable. If I chop off this ethyl, I'll still be left with a primary carbocation, which is not very stable. But if I chop off a propyl group, then I'll have the positive charge on this carbon, and I now have a tertiary carbocation, which is much more stable than the other two. And so for this molecule, we might expect that the base peak would appear at M-43. By chopping off this propyl group and detecting this carbocation fragment, this is most likely the most stable fragment when we chop this molecule up into pieces. And so one thing that we'll provide for you on quizzes and exams where you're analyzing mass spectra is this table. So while these aren't that hard to calculate, you don't have to memorize them or anything. We'll tell you, we'll give you this table, and so you can look, right, for any big peaks, calculate the difference between that peak and the parent ion peak. If you get a 15, probably a methyl. A 29, probably an ethyl, and etc. Okay, so just a couple questions on this video before we move on to the next one. So we're asked to determine the molar mass of the compound. We're asked to identify the base peak and identify any fragments or any peaks that represent the loss of common fragments. And so for the molar mass, I'm looking for the peak that's farthest to the right on the x-axis. And so in this case, it would be the 101. Now, when you answer this question, don't just say 101. Whenever, or almost always, when we give numerical values, we need to have units on it. And so these units are either in atomic units, or the equivalent numerical value would be if we use the units grams per mole. I think that's more commonly used in chemistry, so you can certainly say the molar mass of the compound is 101 atomic units, but I would probably say that the molar mass is 101 grams per mole. All right. The second thing they want us to do is identify the base peak. The base peak is just the peak with the largest intensity, and so this is our base peak. All right, and then the last thing they ask us to do is see if we have any common fragments. And so to do that, we'll find the difference between the parent ion peak and each of the major peaks in our compound. So for this peak, right, I would do 101 minus 86. That gives me 15. And if you remember from that chart, so this is an M minus 15 peak, and so that corresponds to a methyl fragment. Okay, and then if we look at this peak, and we do 101 minus 58, that gives us 43, right? So this is an M minus 43 peak, and if you look at that chart, this is most likely due to the loss of a propyl group. And so I should say this here for the methyl, right? The M minus 15, that means that the peak that we're observing has lost a methyl. It's the peak at 86 isn't a methyl group, right? It represents the loss of a methyl group. And this peak at 58 represents the loss of a propyl group. All right, so one more video with an additional topic, and then we'll look at some examples.